Hello and welcome to lesson number 1 in Unit 2A. This is trigonometry. We're going to start specifically with right angle trigonometry. First, however, we're going to spend the first lesson or two talking about sort of the foundation of trigonometry and what makes it work. So trigonometry is the study of triangles, and we're going to start by looking at a prerequisite skill that we're going to need before we examine similar triangles, and that prerequisite skill is working with ratios and proportions. So let's just jump right in. As it says here in the introduction, a ratio is a comparison of two quantities with the same units. When two quantities are equivalent, this is called the proportion. So what you see here is 1 over 2 equals 5 over 10. Each of these sides is a ratio. Combined, we call that a proportion. Okay, so the question asks us to use cross multiplication and prove that the following ratios are equivalent. So cross multiplication, as you recall, is the act of multiplying the numerator on the first side by the denominator on the second side, and the denominator on the first side by the numerator on the second side. So let's work that through. That gives us 1 times 10. 1 times 10 equals 2 times 5. That is 10 equals 10. And we can say, therefore, 1/2 and 5/10 are equivalent fractions. And this is something that we're going to need to be able to do, not only proving that two ratios are equivalent, or two fractions are equivalent, but also being able to find missing values. And that's what we're going to move on to do next. So we've used cross multiplication now once. Now we're going to use it to actually solve for a missing value. So let's start right here. If we have x over 5 equals 6 over 7.5, and we're being asked to solve for x. So the way to do that is to use, as instructed, cross multiplication. So numerator of one side by denominator of the other, denominator of the first side, numerator of the second. So we have 7.5 times x, which is 7.5x, and that's equal to 5 times 6, which is going to be 30. And now we have 7.5x. How do we isolate x itself? We are going to divide both sides by 7.5. And we have then x equal 2. So let's grab a calculator, because we are allowed calculators in this unit. 30 divided by 7.5 is going to equal 4. So we have 4 as our answer for x. A slightly different way to write down a ratio is like this, where you have, it would read 7 2, as in TO, 9, equals 98 to x. But no need to keep it in this form. We can actually tip these ratios forward and write it as 7 over 9 equals 98 over x. And again, from here, we can cross multiply. So just remember that if you're ever given a ratio sort of in a horizontal form like this, you can just sort of tip it down. The first values become the numerators, the second values become the denominators. So let's get to some cross multiplying here, shall we? So we have 7 times x is 7x, and 98 times 9 is going to be 882. And now again, to isolate x, we're going to divide both sides by 7. X is then going to equal, let's ask the little calculator here, divided by 7, that's going to give us 126. And this is how you use ratios and proportions to find missing values. That's sort of a setup for us. We're going to be needing that as we move forward. So let's move forward. Let's talk now about similar triangles. Now, similar triangles is a concept you would have heard before both in elementary school and in grade 9, but now we're going to explore it a little bit more deeply since we're going to build this whole world of trigonometry on top of it. So what makes two triangles similar? Well, for two triangles to be similar, corresponding angles must be equal. So that's what it reads right there. So let's grab some colors and make this happen. So it says corresponding angles must be equal. So if we're looking at these two triangles, let's start by looking at angle A. It's nice when the shape is sort of identifiable like this, and we can identify that angle A, its sort of counterpart in the larger triangle, is going to be angle D. And similarly, angle B, its counterpart in the larger triangle is angle E. And lastly, angle C has a corresponding angle in angle F. So let's take a moment to write that down. Angle A will be equal to angle D, angle B will be equal to angle E, and angle C will be equal to angle F. So if these three sets of angles are equal to each other, the corresponding angles are equal, then we can say two triangles are similar. And let's see how we write that down. So we would write then triangle ABC is similar to triangle DEF. So there's a couple of things to unpack here. The first is that this little sort of like worm-like squiggle thing, that is called a, it represents similarity. So we would say is similar to dot dot dot. So that's what that little symbol means. And another thing I'd like to point out at this moment is that when you're talking about similar triangles, you must follow them around the triangle in the same way. And here's what I mean by that. If I have triangle A to B to C, and then obviously it would close, so they're all going in this direction, I need to start from the same equivalent angle to A, which is D, move in that same direction, move in the same direction, and then close it up as well. It wouldn't be that proper to say angle or triangle ABC is equal to triangle DFE or triangle EFD. There's really only one right answer when you're talking about similarity, although depending on how you work your way around the triangle, there could be multiple right answers. It's just that for triangle ABC, there's only one. But for triangle, you could write the whole thing in a different way. You could say triangle BCA is similar to triangle EFD. And building on that, when we're talking about sides then being proportional to each other, we know then that side AB, which is this guy right here at the bottom, side AB proportionally will be similar to side DE. And now let's sort of continue that. If we were going to keep going, we could then move on to say, let's look, for example, at side BC now. Side BC would be proportional to, in our second triangle, again, remembering that directionality is important, this would be side EF. And lastly, into our first triangle from C to A, so triangle or for, side length CA, that would be proportional to, again, keeping the direction in mind, FD. And there we go. So we've sort of mapped this whole thing out, and what we've discovered is that there are three conditions for determining whether a pair of triangles is similar. Now I've written them down here. Now's a good time to hit pause and copy them down. I'm going to talk through them very quickly, and then we're going to go on to do some examples. So hit pause, copy them down. When you're done, come on back and we'll pick it up. You're back. You've copied down the three types of similarity. The first is corresponding angles are equal, and we call that AAA similarity. Again, that one's, to me, that's one of the more obvious ones in that there are three sets of angles in each triangle and they correspond to each other. So there's pairs A and D, B and E, and C and F. Corresponding sides are in proportion. That's a second way of telling two triangles are similar. We're going to actually prove that one as we move forward into the next example. And the last one, two pairs of corresponding sides are in proportion and the contained angles are equal, or SAS similarity. We're not going to look at that one right now. We're going to shove that one a little bit deeper into the unit. So let's go and have a look at something that works with the sides being in proportion. So example 1 says, show that triangle PQR is similar to triangle MON. Then find the scale factor that relates the length of triangle PQR to triangle MON. Okay, so we're curious if these two triangles are similar. Now we aren't given the value of any angles. We don't know what angle P or angle M, R, N, O, Q. We don't have any of those. So for us, we're going to need to rely on the sides here. And as you can see, I've set up equivalent ratios. I've used side PR, again, directionality that way, lined it up over side MN, and I've determined that that's 11.6 over 14.5, which when divided out gives me 0.8. Now we're going to set up the other two sets of sides as well. So let's do that now, and we'll see if they are in the same proportion to each other. So we did PR. Let's do RQ now. So we'll do RQ over top of in this other triangle. So again, RQ is this way. So we're going to do NO would be the next one. And I guess while we're setting them up, maybe we can just do the last set. So that'll be QP, QP, and then in this big old triangle here, OM. OM. All right, so now we fill in some values. Side RQ is going to be 9.2. And side NO is going to be 11.5. Side QP is going to be 12. and side OM is going to be 15. So let's do a little bit of math now. We're literally just going to type into our calculator 9.2 divided by 11.5, and we're going to see what we get. So 9.2 divided by 11.5 equals 0.8. So we have that proportion of R, whoops, that's a highlighter, proportion of RQ to NO will be equal to 0.8 as well. We've matched the first one. That's looking good so far. Let's try the last one. So we have 12 divided by 15. 12 divided by 15 gives us 0.8 also. So we have QP to OM also 0.8. So what you can see is that we've proven by showing that the sides of the triangles are proportional to each other that these two triangles are similar. So we could say, since all sides are proportional, or are in proportion, let's say. Whoops, lost half of that word. Got excited. Proportion. We can say, therefore, let's use our similarity statement here. Triangle PRQ is similar to triangle MNO. MNO. We could also have used the little squiggle symbol if we wanted. And again, what we found here, I'm not going to restate this, but as it asks in the question, the scale factor is 0.8 for us. So we've arrived at another example. We are going to be doing that in our next, in the next part of this lesson. So come on back and we'll see you in part 2.